So on this problem, we're asked how many milliliters of 2.02 molar barium hydroxide is needed to neutralize 13.8 milliliters of 8.81 molar hydroboric acid. So what we'll do, I'm going to do two problems here to help you with this one. So first, let's say we have something similar, but I have sodium hydroxide and hydrochloric acid. You'll notice that what's different here is sodium hydroxide only has one hydroxide, whereas the barium hydroxide had two. But in order for neutralization to happen, you have to have the same number of moles of acid as base. So you have to have the same number of, so the moles of OH minus have to equal the moles of H plus. Well, what can be nice about this is we don't actually have to convert from milliliters to liters, because the units will be the same on both sides. So what you can do with these neutralization problems is you can just say M1 V1 has to equal M2 V2. And this is if the number of hydroxide ions is 1 and the number of hydrogen ions is 1. So that makes this really easy. So we could just say the molarity 1.03 moles per liter of sodium hydroxide times our unknown volume equals the molarity of the second one, which was 0.05 moles per liter, times its volume, which is 432 milliliters, and I can just leave that as milliliters. And so V1 equals 0.5 times 432 milliliters over 1.03, and then I can get whatever that is. Or is that supposed to be 0.05? No, it's supposed to be 0.5. And I get 209 milliliters. So, and my answer will be in milliliters. Okay, so, but now let's say I had something that was like this. How many milliliters of let's make it calcium hydroxide. How many milliliters of 2.3 molar calcium hydroxide are needed to neutralize 52 milliliters of nitric acid? Okay, so you'll notice that what's different here is my calcium hydroxide has two hydroxides, and so I only need half as much calcium hydroxide as I need of the nitric acid. So when we write M1 V1 equals M2 V2, then if this is going to get us the number of moles, or actually number of millimoles since we're using milliliters, we see that the number of moles of calcium hydroxide, each one of these is going to give us 2 hydroxides. So if this is our calcium hydroxide side, the number of moles we'll get here will be 2 M1 V1 equals M2 V2, because each one of these gives us 2 hydroxides. So this will be 2 times 2.3 times V1 equals, I needed to have a molarity here, let's say 1.5. 1.5 times 52, or V1 equals 1.5 times 52 over 2 times 2.3. and that gets me 16.96 milliliters. Okay, so this question we're supposed to get the most preferred structure for the phosphate 3- ion. So rather than doing that one, we'll do the sulfate ion. And so sulfate 2- ion. So we need to know the number of valence electrons for both sulfur and oxygen. So when we look at a periodic table, we see sulfur and oxygen are both in column 6A, so they both have 6 valence electrons. And so we know we have a total of 6 from sulfur plus 24 from oxygen plus 2 more because it's a -2, so that gives us 2 extra electrons. So we have a total of 32 electrons to work with. The least electronegative will be in the center, which would be sulfur. And we know that sulfur can expand its octet, and we know that because it is in row 3. So anything in row 3 or below can expand the octet, so it can have more than 8 electrons around it. Oxygen cannot. Oxygen can only have 8 electrons because it's only in row 2. It does not have those d orbitals to expand into, but sulfur can. And we know that our total ion has to have a charge of 2-. So I will have bonds like that. And then let's just start by saying everybody gets 8 electrons and see what happens. So 2, 4, 6. So each oxygen has 6, so that's 24. Plus I have 4 single bonds, so that's 8. So that's 12 carry on, that's 32. Did I add wrong? Okay, so we've got that as a possibility. But let's figure out formal charges on things. So formal charges, you take the number of valence electrons it has, and you subtract the number of electrons, the number of valence electrons it normally has, and you subtract the number of electrons it has around it, and each bond counts as 1. And so for each oxygen, you would have 6 minus, and they've got the 6 electrons around them plus 1 from the bond, so that'd be -1. So each oxygen has a formal charge of -1. Sulfur would have 6 minus 4, because each bond is 1, so that would give us 2. So you give a charge of +2. Now we know we're going to need to end up, the sum of all the formal charges has to be -2, because the whole ion has -2, but we would like to have as the smallest amount of formal charges on things that we can, and so this is not that good. So let's see what happens if instead I take a pair of electrons and move it to there. So now I would have So I still have 32 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. But now my formal charges are -1 on each oxygen, each of those oxygens. This oxygen has a formal charge of Now 1, 2, 3, 4, 5, 6. 6 minus 6, a formal charge of 0. And sulfur has a formal charge of 1, 2, 3, 4, 5. 6 minus 5 plus 1. So that's better. So a smaller number of formal charges. What if I move yet another pair of electrons in? Now each of these oxygens has a formal charge of -1, but these oxygens have formal charge of 0, and the sulfur has a formal charge of 0. So my entire ion has the correct charge, but I've made my formal charges as small as possible, and so that makes this one balance out, and so it gives us the smallest number of the smallest formal charges. Now there's nothing special about which oxygens get the double bond, so this one is actually in resonance with 5 other possible structures that look like this. And so on. You can come up with what the other structures are. But that would be the best structure for sulfate. Alright, and let's see.